Welcome everyone to this special session on the liquefaction-induced hazard effects on buried utilities. This is organized by the SimCenter Working Group on Regional Simulations for Lifelines and Transportation. I'm Jonathan Bray, I'll serve as your host today. And this work is supported by the U.S. National Science Foundation. As you've joined, you realize that there's a motivating factor. Our cities are vulnerable to fire. Some of these can be initiated because of the performance of buried utilities. And of course, we need our buried utilities to suppress the fire once it occurs. And so an important element here is the seismic performance of our buried utilities, and in this session, how they're affected by liquefaction. And so the SimCenter is an organization that is promoting, exchanges of information and technologies and tools to be able to do simulations. And today we'll talk about recent advances in developing seismic risk methodologies and open source software that's available to allow you to develop quantitative estimates that include characterization of the uncertainty so that you can do a proper risk assessment. And it's really exciting to have the presenters that we have here today. Professor Tom O'Rourke from Cornell University has been awarded the Rankine Lecture, the Hausner Medal, member of the National Academy of Engineering. Tremendous landmark work he's done over his career in Lifelines engineering. Dominic Asamaki from California Institute of Technology, winner of the Casa Grande Award from ASCE, the Young Researcher Award from the Earthquake Geotechnical Engineering Committee in the International Soil Mechanics, and a principal player in terms of the work of the CEC project that was directed down in Southern California to look at this problem. Caterina Ziapatullo, who's a professor at UC Davis, also a winner of the Casa Grande Award and the Young Researcher Award from the Earthquake Geotechnical Engineering Committee of International Soil Mechanics and Foundation Engineering, and a co-developer of the widely used models PM4 Sand and PM4 Silt. Barry Zheng, who is the developer of the open source software OpenSRA that will be discussed today. He's an engineer at Slate Geotechnical Consultants. And Jinyan Zhao, who's a member here at UC Berkeley, the NERI SimCenter, and an expert on several things, but especially R2D, which is a regional-based tool that can be used to look at risk. And so we're looking forward to their discussions, and then we'll have a discussion afterwards. So presentations and then discussion. So that you participate and your questions are answered, please use the QA button that's shown here. You can ask a question at any time. You can send that to us, and then we'll bring that in and we'll weave that into the panel discussion that we have after these talks. If you find a certain question is particularly interesting, you can upvote that and you can engage in the chat, but the QA function is what we're using to collect the questions for the panel session. I'll start off with some initial topics that we have developed that we know that are important, and then we'll bring in your questions. So please do present those questions and we'll take care of that. For those of you that have just participating in SimCenter for the first time, it's a National Science Foundation funded NERI Center. This is the website that you can get from the slides, but please join. You'll get an email asking you about this as well. But this is your organization to serve your needs in research and in practice in terms of being able to do certain things. We're focusing on pipelines and liquefaction, but there's a number of different types of things that are covered. And in fact, just to give you some heads up, some upcoming events tomorrow, there's actually a roundtable that's focused on modeling of site buildings and bridge system performance and regional earthquake simulations. There's another community roundtable in November, and there's the symposium held at UCLA in early February 2025. So without further ado, I'd like to start with Professor Thomas O'Rourke.
Hi, I'm Tom O'Rourke. I'm just going to set the presentational mode here. There you are. You should be able to see the screen right now and my cursor. I'd like to begin by acknowledging the great team at OpenSRA and the SimCenter. And I'd like to, in particular, acknowledge Chris Bain. He has contributed a lot of what I'll show today, John Bray and Norm Abrahamson. So on the lower right-hand side, you see a fire at the Balboa Boulevard. And that fire was actually in a nominal 6-inch diameter gas distribution main. If we actually look to see what caused the fire at Balboa Boulevard, it was the rupture on the left of this gas transmission pipeline, which was approximately 20 inches, excuse me, in diameter. And that set a fireball in the air, very similar to what we see on the right-hand side with respect to Hellgate in New York City. So ultimately, when we talk about violating the pressure boundary, we talk about strains where we believe that there could be a significant opportunity for rupture. And if gas under high pressure gets out and finds an ignition source, you can have a very significant event. And clearly people want to avoid this sort of situation. You'll hear a little bit about tiered assessment approach, but we're going to look at Balboa Boulevard. Myself and Katerina, she will present on some of the soil situations. I'll talk about the pipelines. This is an advanced analysis, and it's a case history that allows us to calibrate a lot of our tools and understand the importance of both conventional and risk-based analysis. Balboa Boulevard site is in Southern California. This is showing the fault plains and the epicenters for the 1971 and 1994 Northridge earthquake. In 1994, there was a zone of ground deformation, a block-type deformation on Balboa Boulevard from north to south. Here's the tensile deformation zone. Here's the compression deformation zone. If we take a closer look at these pipelines, you can see that the movement is from north to south. So over here on this side, we have a tension zone, we have a compression zone. And unfortunately, this picture, the north is on the right-hand side, the south is on the left-hand side. So the movement is actually in this direction from north to south. The displacement's about 20 inches or so, and the length between the tensile and the compression rupture zone is about 935 feet, or about 285 meters. These are some pictures to give you an example or an idea of the kind of damage to the pipeline facilities that this ground deformation caused. There was a Granada trunk line, one of the major trunk lines for the Los Angeles Department of Water and Power, distributing lots of water under significant pressure in various parts of the city. And in the tensile zone, it actually pulled apart at a dresser coupling, and you can actually measure that displacement about 18, 19 inches. And that was part of characterizing the ground deformation, because that actual pullout should be very close to the average movement of that soil block. And here is a Granada trunk line in the compression zone. And the compression failure initiated at the welded slip joint, which began to buckle and then generated additional buckling and evidence of compressive deformation. On Balboa Boulevard, there were 8 different pipelines for water, for natural gas, for oil, and for other kinds of gas lines. And of these 8 different pipelines, they were subjected to the tensile deformations, and they were subjected to the compression deformation, and about half of them failed. So you see old line 120, which started that large fire, natural gas distribution line, the Granada water trunk line, and the Rinaldi trunk line, all had failures, and the other ones, the other 4, didn't fail. They didn't find any damage associated with these lines. So this is a superb case history, because it samples the response of some very interesting and important lifelines. We have a model for soil block movement. It's a closed form solution. It was developed by Mike O'Rourke, not me, by Mike O'Rourke, who for many years taught at RPI. He's now an emeritus professor there, and Jack Liu. And essentially, their model in closed form treats the soil as a soil block, and that soil block displaces in a particular direction, in this case, from north to south. And that soil block is subject to a certain amount of displacement, which puts the ground and the pipelines into tension and compression. Using this closed form solution, one can evaluate or analyze what the axial pipe strain actually is. And one then can compare that to the critical strain, that is the strain at which we think that rupture would occur if you exceeded this particular value. Also, the OpenSRI team looked at the effects of different couplings and of different anchors and changes in angles in the pipelines which act as anchors, and actually extended this model and was able to show some additional interesting features. If we were doing a deterministic analysis, we have a number of analytical models that we can break down into different variables, such as those associated with ground and pipe dimensions, the soil, then the pipeline itself. And we would give our best estimate of these values, and we would come up with some sort of a longitudinal or axial strain, and we could compare that to the critical strain. And that would be a known or an estimated set of values. But we can also look at these as statistical distributions. And so we can perform these analyses 100,000 times in terms of simulations, Monte Carlo simulations. And therefore, we get a standard deviation and a mean associated with these parameters. And you can sample this information and then get a distribution of longitudinal, tensile, and compressive strains. You can compare those to the fragilities to determine the range of the probabilities of failure. And then you can compartmentalize these probabilities by expressing them in terms of percentiles, which help us judge the degree to which the information is constrained. So we can take these models. We've taken the Mike O'Rourke and Jack Liu model, and we can calculate the maximum pipeline strains. Notice that we not only looked at strains generated by block movement of the ground triggered by soil liquefaction, but we looked at the transient motions, that is the maximum transient strains, the seismic wave effects. And in general, which is most interesting, these are 1 to 2 orders of magnitude less than the strains generated by permanent ground deformation. And so when you sub the two, they are very much reflective of the permanent ground deformation. Anyway, these strains can be compared with the critical strains. And as I'm showing on this particular diagram, you have old line 120, distribution line, the Granada trunk line, and Rinaldi trunk line, all having strains from our model which exceed the tensile strains and compressive strains, and therefore are the locations of failure. Some very interesting work has been done to take a look at buckling of pipelines. And Chris Bain was able to put together a plot of the critical pipe strain, that is the strain at which we would expect buckling and deformation leading to unsustainable strains to occur. And he's showing that as a function of D over T. He's taking a database that's based on laboratory tests that were run by Moore, about 196 different points. And from this, one can calculate the standard deviation of the residuals. And as a consequence, you can calculate what the aleatory uncertainty is. And one can look at the intersection with the y-axis and take the standard deviation of that. And one can therefore determine what the epistemic uncertainty is. These can be put into probabilistic pipeline response, where we have the probability of pipeline wall buckling as a function of pipe strain. You can see for the median value and for a D over T of 20, you have this shape associated with the aleatory uncertainty, and the range going from the dashed lines here associated with the 10th and 90th percentiles, showing how well the data are constrained. We can take a look at the probabilistic pipeline response. You can look at conventional results where you actually would normalize the critical strain by virtue of the maximum strain. And when this value is over 1, as it is with this old line 120 and line 170, you look at the probabilistic responses, and there you have 0% of chance of failure. But when this value is very small, you have 100% chance. So these agree reasonably well. And what we show in the probabilistic response is the same for most of the pipelines as we show in the probabilistic response and in the deterministic response. But we do note that there is a probability of compressive failure of about 69% in line 3000. And what's nice about the probabilistic response, one can work with the tornado plot, and the tornado plot for line 3000 shows that the 75% of the uncertainty is with the critical compressive strain. So you can see that about 40% is the aleatory and about 35% is the epistemic uncertainty associated with this condition. So we would expect that even though we didn't see compressive failure and we forecast compressive failure or buckling at this pipeline, there is a lack of constraint on the epistemic uncertainty, and therefore a probability that they could or could not have compressive strain failure. And this comes from a probabilistic analysis and allows us a much deeper dive into the response of the ground. So the final slide is just a summary. This case history at Balboa Boulevard is really as good as it gets. You have high quality data on the pipelines, on the groundwater, and the displacements. Katerina will speak more about some of these. We have a closed form analytical model which mirrors the circumstances extremely well on Balboa Boulevard, and we can use that to predict or to give us what the longitudinal strain is compared to the critical strain. Conventional and probabilistic assessments predict observed tensile and compressive performance of 8 pipelines, with the exception of compression in line 3000. But we've seen that the probabilistic response accounts for this and shows that there are a wide range of possibilities for this particular pipeline. And we have the tornado plots, which show us that 75% of the uncertainty is in the critical compressive strain. And we also recognize that if we were to include cyclic softening of some of the clay-like backfill material, this will actually diminish the shear strains between the soil and the pipeline, and therefore diminish the strains that would be in the pipeline. And that would very much go a long distance in explaining the performance of line 3000. So that's what I have to say. I look forward to the different panel discussion that's going to occur on this. And I thank you for your time. And I will share or stop sharing my screen. Thanks very much.
Thank you very much, Tom. We're now move to Professor Dominiki Asamaki from Caltech.
Good morning, everybody. Let me go into the presentation mode. So I will present you the work we've been doing as part of a project that was funded by the California Energy Commission. As it is the case usually for faculty members, the work was actually done by 2 members of my research group, 2 postdocs, Grigorios Lavertiadis and Zach Bullock. The group that was tasked with studying the ground failure displacement hazards in California associated with the failure of gas pipelines is outlined here. So this was a much bigger project. And we were tasked specifically with studying the liquefaction risks of pipeline systems. This slide shows the extent of the pipeline networks that we were looking at, but we were aware also that the type of failures that we were tasked to look at still corresponded to localized problems like the one that Professor O'Rourke just showed. So despite the fact that the network was distributed, we still had to account for the fact that the failures that we had to evaluate were localized in terms of risk. So the innovations that I'm going to present you today that our team came up with in order to address the conundrum that we were, on one hand, we have a very extensive network to study, and on the other hand, we still had to come up with solutions that address localized failures. Were twofold. One was that the established liquefaction procedures that geotechnical engineers have been coming up with in a long time require site-specific information, so correlations with SPT or CBT tests, but these are either not available or too expensive for us to expect to have for regional problems. So here over the entire state of California. And on the other hand, the geospatial methods that are the geological equivalent of the geotechnical methodologies do not address the extent of the liquefaction area. So they are as generalized as the geological units themselves. And one cannot expect that the extent of liquefaction, given all the distribution of the peak ground velocity or the geological unit VS30 and the water table level, will be as extensive, for example, as this geological unit over here. So that is, however, as you saw in the previous slide, the failures that we had to address was localized. So I cannot expect to predict that the liquefaction extent will be over a kilometer square. So this is a key component of risk for distributed infrastructure. So no matter how large the probability of liquefaction is predicted by the geospatial methods, I still have to be able to say that it's going to be probably here and here and here, and the here has to be over a specific location. So the workflow that we came up with to try to merge the knowledge of the geotechnical engineering community with the understanding that we still needed to take advantage of regional scale geospatial information is the following. We took advantage of information like digital elevation maps that were given to us by CGS, geologic units. Here is the WHEELS map of 2015. Several locations of wells where we had detailed measurements of the depth of the water table. It wasn't everywhere in the state of California, but as you can see here, it's very, very dense. Everywhere wherever we didn't have, we had other means of evaluating the depth of the water table that I will present to you shortly. And some clusters of CPT measurements that were very, very strongly correlated with areas of high density of population, right? So in San Francisco and in Los Angeles, we had a lot of CPTs, and then in between, we had very few. So we identified areas with potentially susceptible soils and shallow water tables. So we were able to find a way to identify where the soils were susceptible. We proceeded there with identifying liquefaction analysis, triggering and the effects thereof. We came up with a process of deriving a latent Gaussian process to distribute the percent of liquefaction from the geospatial units into features. So take the percent of liquefaction and have a data-driven approach to distribute this into clusters that are driven by data from past earthquakes, which matters to risk. And this is a published work that I will present to you shortly. And then within each feature, we were able to compute displacement probabilities. So in more detail, for the step one, our input we had twofold input. We had local conditions, so the information of the DM, the geology, the VS30, and then the clusters of CPT and the location of the wells. And then we had ground motion information, PGAs and PGVs. Our team recognized very early on that we needed to have scenarios of peak ground acceleration, peak ground velocities. That the hazard alone was not enough for us to establish the spatial variability of ground motion. That is important for us to establish then the spatial variability of the intensity measures that go into the risk of the liquefaction effects, such as the displacement. And then we had the modeling workflow that identifies the areas of liquefaction susceptibility. And from there, we didn't want to reinvent the wheel. We wanted to be able to take into account the knowledge of the geotechnical engineering community, but then be able to spread it in a data-informed way over the entire state of California. So we wanted to be able to use the liquefaction triggering and lateral spread and settlement models, but we wanted to be able to do that in an intelligent way in order to come up with deformation measures. And if my mouse worked, I would show you how we did that. So the first thing is to account for epistemic uncertainty. We did use everything under the sun in terms of we accounted for the availability of CPT profiles, the different means that we had of water table. One was the availability of wells. In absence of availability of wells, we used the global water table models, different models for susceptibility, different models for triggering, and then in the end, different models for deformation, be that settlement or lateral spread, and the separation of the two was defined based on whether the point that we were studying, the grid point, was on a slope or on flat ground. How did we use the CPT data? Now you can see they're not evenly distributed, so doing anything resembling kriging or something like that, interpolation would be pointless. So the way we approached the problem was we clustered them based on geologic units. And the clustering was, so we found what CPT measurements were in what geologic units, and then we create dendrograms on those CPT data within each geologic units, and we identified them based on the location of the CPT and their corresponding, tagged them with their corresponding VS30. And so within the geologic units, we had clusters of CPTs with different groups of VS30. And so now if I have a point within its geologic unit, and that point is located in a specific location that has a given VS30, then there are different probabilities that this point will have different VS30 profiles based on random fields that we developed from data that we collected from the Bay Area and from different locations in Southern California. So now I am able to take a point in any area in between those two and come up with random realizations of those CPT profiles and weigh them based on the VS30 of that location, based on its location within a geologic unit and the VS30 of the site. And now I can go back to my logic tree and plug in the different probabilities of the CPT realization and it's the tip resistance and its slip friction. And now I can use the engineering, the geotechnical engineering approaches for triggering. In terms of the water table, if I am located, lucky me, on top of a well, then I can use the measurements of the well. And in fact, if it is a well that was measuring water, the water table in the recent years, then I can use, in fact, the measurements that was done last year and weigh those more than the measurements that were done 10 years ago. But if I am in a location that has no wells, for example, right here, then I can use the global mode of the water table. And if I am in a location that is close to a well but not on top of it, I can weigh the well measurement a little bit and then the water table more, depending on whether I'm closer to a well or further away from it. So we developed a weighing mechanism to take into account the available data when I was close to it, or the global model when I was further away from it. So I would use as much data as I could, but I would not only rely on data when I didn't have it. So armed with this workflow of using the geological unit and the VS30 to be able to do realizations of the CPT data, the global water model and the water table from the wells, to be able to weigh the two and use as much as I can to represent the depth of the water table. I can simulate random fields of CPT. I can calculate the profiles of the intermediate variables as if I am now at a site that I have a measured CPT depth. I can evaluate the soil susceptibility using every method in my logic tree, do the triggering and the deformations, a median and a standard deviation using the PGA as a function of PGA. And now for every scenario realization that I have from the hazard curve through the scenario realization methodology of Wang et al. In 2023 that our team developed, a different group of our team developed, I can now go back and estimate displacements and settlements. Before I do that though, how do I go from a map that has a PGA distribution that is relatively coarse and a geologic unit distribution that is relatively coarse to a distribution of the probability of a distribution of the area of liquefaction that corresponds to the localization of the damage that Professor Rourke was showing before? I still need the space variability to be able to correspond to the risk of the distributed infrastructure that I'm studying. For example, that will matter because this is the area of liquefaction is 20% of the total area here and 20% of the total area here. But if I have two pipelines crossing, those two will not have the same amount of damage. So we use data from previous earthquakes, and we were able to develop a Gaussian process that creates a correlated field with patches that are data-driven and is able to distribute this probability of liquefaction in space in a way that is data-informed, and takes the geospatial model and spreads it out on the basis of the results that we get from the regional distribution. So to show you that's my one slide before last. For an example scenario in the Santa Susana Mountains in north of San Fernando Valley, in an area that has alluvium units and the water table shallow, so it has a lot of liquefaction susceptibility. We are able to, this is one realization of a PGA map for a hazard for a magnitude 8, and this would be the PGA distribution for one realization you see here on the left. I am able not only to build clusters of settlement and lateral spread and find a range of displacements, but also tell you where there is settlement and where there is lateral spreading, and they are clustered together so I can have lots of different realizations of those and find distributions of displacements and lateral spreads and the risk on distributed infrastructure. Thank you for your patience and thank you for your time.
Thank you, Domeniki. Now we'll move to Professor Katerina Zivatulu from UC Davis.
Okay, forgot to unmute myself. Okay, so greetings from my end as well. I'm Katerina Zivatulu, and my presentation is going to take us back to the Balboa Boulevard case history. So we're going to stay at the foothills of the Santa Susana Mountain that Domeniki left us at. And I'm going to re-talk a little bit about that case history, focusing more on the soil side and some of the advanced numerical modeling work that we have done, elucidating some of the soil failure mechanisms. This work would not have been possible without Ranman Patel, who's now an assistant professor at the University of Nevada, Reno, and Dr. Craig Davis, formerly with LADWP, who provided great insights based on his familiarity with the area. So thanks to Tom, we're very familiar now with the area. We have these progressively zooming in plan views. This is the Balboa Boulevard area of interest. And on this map, I'm also showing to you some of other famous locations in that area. The closest recording in the free field is a Rinaldi receiving station, a ground motion with very distinct signatures that most of us would be familiar with. Tom covered the whole extent of the pipeline failures in that area. I want to focus on the two water trunk lines that failed with diameters of 1.24 meters and 1.73 meters. I'll be showing them to you in the slides that are following up. We will see some numbers later in terms of compressive shortening in the scarp where compression was observed. We're talking about 25 centimeters of compression. Taking another look at the plan view, but now focusing a little bit on the two trunk lines. This is the Granada trunk line and the Rinaldi trunk line originating at the Los Angeles Reservoir, and they're both meeting a little north of our site of interest, and then traveling together south and then making a right on Rinaldi Street. And this is a plan view of how they were positioned underneath the boulevard. Now my north is going to be to the left. So this is a counterclockwise rotation off the street, and we're looking a little closer to the two locations of maximum extension and maximum compression. Tom covered these very nicely, so thank you for that. But we're also seeing here some of the ground cracks that were observed after the earthquake. There have been different numbers reported by different entities in terms of the openings observed: 45 centimeters in the extensional zone, 50 centimeters in both zones, 33 to 54 in extension, and 27 to 42 in compression, and a larger range, of course, from aerial photographs. And some of these were recorded on from field reconnaissance and adding up some of the openings measured. We already saw the picture of this failure, and it's coinciding a little bit with the opening scarp there in an extension, and this is one of the compressive failures. And if we take a record of the types of failures that were observed, you saw some of these, but not with these codes in Tom's tables. When you see R, it is referring to the Rinaldi trunk line. When you see G, it's referring to the Granada trunk line. So this one was G6, and this telescoping failure was in G7, just at the south side of the headscarp boundary here in the compression zone. And of course, we have failures observed outside of these locations of ground failure that still need to be studied, and I'll be talking about that in a little bit. There were two more failures further to our north, but we do not believe that these correlate with this mobilization that was observed here. And here you see a little bit of a sneak peek of the numerical modeling boundaries that I'll be showing to you in a bit. Going back to the plan view, again, we see the pipeline axes. There were two site investigation campaigns on the east and the west alley. This one was from SoCalGas, and this one was from USGS. This data is publicly available. And if we combine this information with the alluvial environment we're in and the orientation with which these depositions have been made, we project all of these together in one cross-section. Just for reference, for those of you familiar with simplified liquefaction analysis, the Balboa 10 CPT sounding is the one that has been used in the past for simplified liquefaction analysis and effects assessment. This is the cross-section of the site. Now here we see all of the information projected in one cross-section. 4 different units were already identified by prior researchers in the mid-90s, right after the earthquake. And the different colors you see here in the different soundings are the assignment of sand-like, clay-like, or transition soils based on the I/C index found. Now, from the data that we have here, we believe that the I/C boundary between sand-like and clay-like must have been a little higher than 2.6, and this is something that we evaluated later. Of particular importance is the location of the water table, which is saturating some weak soils here. We'll be looking at these later. And also the zone where the water table is saturating, this unit C, these are the alluvial depositions, aligns with the zone of maximum extension. And the location where the water table is going deeper is aligning with the location of maximum compression. So the mechanism of failure is very plausibly just a sliding mass, opening a ground crack here and a compressional zone here. And with such a failure mode and the displacements measured, the failure of the pipelines broadly is not a surprise. Now, fine-tuning and understanding some of the magnitudes there is quite important. The hypotheses back in the day where it could be either liquefaction or cyclic softening of lean clays, and some less popular but equally reported thoughts related to seismic compaction and the co-seismic displacement. But we performed advanced numerical modeling to elucidate the potential roles of these two modes of failure. We collected all the data subject to different considerations of I/C. Here I'm showing the assignment of undrained shear strength just for one sounding and then collecting all the soundings in the area. In order to pick some properties, we started with some median distributions and picking the 50th percentile. But I will say that if you isolate the soundings that are in the saturated zone, the SU, the median SU, would not have been 80 kPa. It would have been something like 50 kPa. And this is something also to be addressed. Same process for the sand-like portions, a little less uncertainty here. A more narrow band of QT1 and CS values and the implied median relative density with some considerations about this transformation was about 50%. So we performed advanced nonlinear dynamic analysis 2D in FLAC 8.1 and currently in FLAC 2D. Very large model here. It's vertically exaggerated, so the slope was just a 2.6%. And we paid particular attention to the alluvial deposits here. Anything you see green is a sand-like soil, and anything you see as red is a clay-like soil. And then the volumetric participations here represent an I/C of 2.6. In order to do these stratigraphic realizations, we did transition probability geostatistics. So basically conditioning from CPT to CPT, we evaluate the probability of transitioning from one soil unit to the other. And you can generate many realizations to have some better statistical representation. But regardless of how many realizations you get, the CPTs are always going to be honored. We assigned the constitutive models PM for sand and PM for silt in the sand-like and silt-like materials. I will not go over the details of those calibrations. But now in terms of results, we do get some high excess pore pressures right around the area of the Balboa 10 sounding, unsurprisingly. And we do get maximum shear strains that tend to go in the direction of really high mobilizations. Now, of course, this is a continuum approach, so we cannot get any discontinuities on cracks, and we did not do any soil structure and interaction analysis. We only focused on the soil because we wanted to see what is happening there. In terms of displacements and given the limitations that I just mentioned, just for a baseline analysis and median properties, just few realizations, an I/C of 2.6, the maximum displacements observed are of the order of 35 centimeters. But what is worth noting for these types of analysis and evaluating a little bit the value that they bring to what we do is the ability for us to see what happens throughout the seismic loading history. And in the bottom plots, I am showing stress strain loops at 3 distinct locations, 2 clay-like zones and 1 sand-like zone, and they are color-coded with a temporal alignment with what is happening in the time history here in the pre-pulse phase, during the pulse, and then afterwards. And for all 3 locations, we can see that during the pulse, and also that is not very surprising, but I find it's always cool to look at what we can get from these types of models. And what we learned from this one is that, yes, it was liquefaction, but it was also cyclic softening, which Tom mentioned. And if it wasn't the sands being so close to clays that were softening, we wouldn't have gotten such a large mobilization. We later did parametric investigations just to start seeing where we land. And of course, these are maximum horizontal displacements and by no means what we would have gotten if we had a discontinuum, I guess, approach. Our baseline analysis of the 35 centimeters that I just talked about, evaluating what different I-sub-Cs would have gotten, honoring the lower SU that I mentioned before also raises the numbers, and it's plausible. And then doing an alternative calibration of the models, also focusing on cyclic mobility, gets us closer to the median, but also gives us a broader range of uncertainty, which is important to know. Now, I mentioned that we did not do an SSI analysis, but we are looking at the smooth horizontal strains at the ground surface, or better at the burial depth of 1.35 meters. For multiple realizations as a proxy of the failures. The patterns are generally consistent, but we are observing 2 zones of extension, and these are at the end of shaking. So what we're doing now is we're looking at the timing of strains just to see what happened first and where the failures may have started. And a parting thought, we did this model here because that's where we had soil data. There are other failures of pipelines that are not at least visibly justified by ground cracks. So it's worth to look at what happens to the north and how these failures may be justified with some more extended soil models. My concluding remarks, just is there a benefit in doing 2D NDAs? I believe yes for this case, perhaps not for every case, but without doing them, we wouldn't have seen that it was actually the contribution of both types of soils. And as reasonable our choices have been, they all carry uncertainty. So, and this is also something worth exploring. For future work, we are looking at the transient strains and looking at some other neighboring locations. Looking at the pipeline damages, which Tom talked about, can narrow down some of these parameters, but also we must recognize, but some of these complexities are trivially encountered in engineering practice, and we should be considering them as we develop design criteria. With that, thank you very much.
Thank you, Katerina, and we'll now move to Dr. Barry Zhang.
Did I stop sharing? Not yet. Okay.
Okay, thank you.
Give me 1 second. Okay, hi everyone. My name is Barry Zhang with Slate, and today I'll be talking about OpenSRA, which is an open source software for seismic risk assessment of natural gas infrastructure. For today's presentation, I'll briefly go over the project and software overview. I'll talk about an example run of pipe assessment at Balboa Boulevard, just to connect with the other presentations, and then finally I'll wrap it up with a summary slide. So the OpenSRA project was funded by the California Energy Commission from 2020 to 2023. The main PIs for OpenSRA 1 were Professor Bray and Professor Abrahamson from UC Berkeley, as well as Dr. Watson Lamprey with Slate. The primary research scope was to develop a new set of fragility models for natural gas assets, specifically pipelines, facility components, wells, and cap rocks, when subject to geohazards in the form of liquefaction, landslide, and fault rupture. And the software that was needed was needed for users to allow users to choose from new, existing, and custom-built models for analysis. It has to be able to interact with common earthquake characterization sources such as USERV3 and ShakeMap, and it has to allow users to use their own data for assets and model inputs. And finally, we have to be able to propagate uncertainty and perform risk calculations very efficiently. Here are the teams for the first OpenSRA project, including Peer, UC Berkeley, Lawrence Berkeley National Lab, UNR, UC San Diego, Slate, Professor O'Rourke from Cornell, and then Ledges Consultant. It is peer.berkeley.edu/OpenSRA, and on there you can find information for the first projects such as publications and products, as well as any news that we will be providing for the new project OpenSRA 2, which I'll briefly mention later. The risk framework that is implemented into OpenSRA is the performance-based earthquake engineering framework from Peer. And for this framework, you start with ground motions such as PGA or PGV, and then you step into system response to estimate ground deformation, and then use that to inform the physical damage in the form of like pipe strains, for example. And then finally, use that to estimate losses in the form of probabilities of leaks and breaks. OpenSRA also uses a tier assessment approach that Tom showed in this presentation. And these tiers are essentially based on data resolution, where the higher the level, the higher the data resolution. So for example, a level 1 analysis might be like a statewide analysis where you use information available at the state level. And then for a level 3 analysis, we might be using data such as CPT to perform more perform analysis with lower uncertainty. And I'll spend the rest of this presentation just going over again Balboa Boulevard and just showing you what OpenSRA can provide. But first, I just want to remind us the findings that are presented in previous investigations, and Professor O'Rourke mentioned a lot about this, but I will point you to the sections of the ground deformation and pipe damage in that for San Fernando earthquake, which I'm comparing to with the Northridge earthquake. For San Fernando, there were no deformation and pipe damage reported or observed. And then for Northridge, and Kyrie mentioned that the deformation was generally about 50 centimeters. And then Tom mentioned that there were 4 pipelines that were damaged, including this Granada trunk line that failed in compression. So very briefly, this is what an OpenSRA level 3 analysis may look like, where we start with USGS shake maps for the individual earthquakes, and then we use CPT-based methods to model lateral spread and liquefaction. So the calculated mean deformations, for example, for San Fernando would be generally less than 5 centimeters for the CPTs, based on the CPTs. And then for Northridge, the mean deformations are generally greater than 5 centimeters. And then OpenSRA uses this information to do something like the figure that I'm showing on the right-hand side here, where the red triangles are the CPTs, the lines are the pipelines at Balboa Boulevard. This gray polygon is a lateral spread deformation polygon that OpenSRA generates based on the mean deformations calculated from CPTs. And then these stars are the locations inferred between the pipelines and the lateral spread deformation polygon. And so depending on the slip direction of this polygon, these crossings may be analyzed as either in tension or as in compression. So very, very briefly on the result. So for San Fernando, OpenSRA predicts probability of rupture of 0, just because the deformations are very small and the strains were limited. And this is consistent with observations. And then for Northridge, so I mentioned that there were 4 pipelines that were damaged, and those are highlighted in yellow here. And for those pipelines, I think Tom showed the same set of results. The OpenSRA predicted mean probability of rupture of somewhere on the order of 30% to 80% for tension and compression. And specifically for the Granada trunk line, the probability of failure is higher in the compressive range and direction. So in summary, OpenSRA is an open source software for efficient seismic risk assessment of natural gas assets. We have a website for version 1 as well as version 2. I will mention that we now have a new CEC grant that's funded through 2027 of the OpenSRA to make use of monitoring data. And then finally, we have also been engaging local utilities, and we have been receiving funding from PG&E to perform validation exercises to facilitate software adoption. Thank you.
Thank you much, Barry. Now we'll move to Dr. Jinyan Zhao.
Hello, everyone. I'm Jin Yan. I'll talk about liquefaction and buried pipeline models in SimCenter software regional resilience determination tool, in short, R2D. Barry talked about the peer and CEC project, and he introduced in a very depth detail about the open source software, OpenSRA. And at SimCenter, we have another regional risk assessment tool called R2D. And in fact, a big part of the OpenSRA graphical user interface is borrowed from R2D, but the backend calculation code of the two software are independent and very different. They are different because by design, R2D has a different purpose than OpenSRA. The first of such difference is R2D aims to analyze multiple type of natural hazard and multiple type of infrastructure. Also, R2D aims to create a flexible simulation workflow. We aim to enable the users to select from multiple resolution and multiple fidelity modeling process in the whole peer probabilistic-based engineering workflow. Reflected on software implementation, these two main purposes of R2D lead to a design of more modular design in R2D than OpenSRA. Also, R2D used the Monte Carlo-based uncertainty propagation method in contrast with the polynomial chaos expansion-based method used in OpenSRA. Just to show you more details of these differences, here is the user interface of OpenSRA, and you can see the liquefaction models are integrated into the main user interface. And when we run the software, the liquefaction models are also integrated in the main workflow, so only the mean and the standard deviation of the liquefaction engine demand parameters, EDPs, are estimated. These EDPs are liquefaction probability, lateral spreading, deformation, settlement, and so on. And these estimated EDPs are directly fed in the downstream PBEE risk assessment using polynomial chaos expansion. And these estimated liquefaction EDPs are not considered as a main output of OpenSRA. Differently, this is the graphical user interface of the software R2D. You can see it shares a similar style with OpenSRA, but all the ground shaking intensity simulation and ground failure models are implemented in a separate toolbox in the drop-down menu embedded in R2D. When I open this toolbox, an independent window will pop up, and in this window, I will go through define the locations of interest, select the earthquake rupture focusing model, select the earthquake scenario I want to analyze, and then I can estimate ground shaking intensity realizations using ground motion prediction equations and spatial correlation models. And we also copied the level 1 OpenSRA liquefaction and landslide models to R2D. So using the ground shaking intensity and other inputs, we can estimate the ground deformation induced by liquefaction and landslides. And in the end, if you want some time history records, you can also select ground motion records from peers NGA Wedge2 database through this user interface. I want to highlight that the output of this toolbox is the intensity realizations instead of the mean and standard deviation prediction in OpenSRA. These realizations are saved in CSV files, and they are imported to the main R2D user interface to do the later risk assessment. In the context of pipeline risk assessment, in R2D, you can use FEMA's intensity measure-based fragility curves to estimate damage measures. You can also give R2D your own intensity measure-based fragility curve database. Interacting with the backend code, you can also define your own pipeline string model and use those string-based fragility curves similar to OpenSRA. By far, it is a standard peer performance-based engineering framework, but R2D can do a bit more. So in this newly added feature, we enabled hydraulic simulation of the water distribution network considering earthquake-induced damages. So you can estimate what's the disturbance to the water delivery surface after an earthquake event. Also, you can simulate the recovery process of this water distribution service. Moreover, in R2D, you can consider multiple types of infrastructure in the same analysis. In the figures below, I estimate the ground shaking, ground failure intensity using R2D. Then I estimate the most likely damage state of all the buildings and transportation infrastructure on this island. And then using a very high resolution recovery simulation package, we can really estimate what's the status of each component in the region along the recovery process after this earthquake event. And in this simulation, we consider the resources flow between different infrastructure components. So we capture the interdependency of different infrastructure layers. So to summarize, comparing R2D with OpenSRA, R2D has a less comprehensive liquefaction buried pipeline model library than OpenSRA, but R2D can do a bit more than OpenSRA. R2D has some other research infrastructure. And the SimCenter website has a lot of documentation, tool training resources for R2D and other research tools. So if you are interested to know more, please visit the website or contact us. And that's all of my presentation. Thank you very much.
Thank you very much. That's outstanding. And thank you all of our speakers for presenting these different kind of views and perspectives on this problem. Let's start off with discussion. One of the things I'd like to start off with, and we'll go in the order that you spoke for this first question, is what matters most in the seismic performance of buried pipelines? What should we be really most focused on, whether we look at it probabilistically, whether we look at it on a regional basis, whether we look at it on a site-specific basis? What are the things that you feel are most important to focus on? Tom?
So I believe that all the work that's been done on pipelines and ground deformations and so forth have left us with the observation that the most important aspects that affect the pipeline are the strains that get generated within the pipelines and the deformations that get generated in the joints or in the special fittings and so forth. So if you have some idea of the ground deformation, you can enjoin the ground deformation with the representation of the pipeline, depending upon what kind of pipeline you're looking at. And you can predict the strains that would be generated within the pipeline. And if it's a jointed pipeline, and this is very important because jointed pipelines are all over the water system. They don't exist in the gas system, but they do exist in the water system. You have to be able to take a look at what the capacity is in terms of pullout, in terms of compression, and eccentricities of load and so forth. So to me, strains and deformations are extremely important. And there's lots of interesting uncertainties. So let's, for example, quickly take gas pipelines. You have older pipelines with oxyacetylene welds. You then have unshielded electric arc. Then you have early shielded electric arc. And then after World War II and all the knowledge that was gained in terms of welding from World War II, you have the modern era of shielded electric arc. So just assigning what the vulnerability is of these different lines is extremely important. Sometimes we know more about ground deformation than we know about the tolerable deformations that could be sustained by pipelines and existing infrastructure.
Thank you. Dominique?
It's really easy for me to say I agree with Tom, but I agree with Tom. And it's evidenced by the fact I was typing a response on the Q&A that I was saying what really matters is the relative deformations. And we appreciated it very much, trying to distribute those patches of liquefaction across regional scales. We came up with this understanding very early on when we figured out that if we're trying to evaluate liquefaction on regional scales, we can have patches of kilometer lengths of liquefaction, of liquefied areas, because that will do nothing for us to translate that into risk of distributed infrastructure. The damage that we see in evidence from I don't know, field observations is still localized. And so what matters really is us being able to translate that into locally relative deformations, i.e. strains of the soil, and therefore with whatever measures we have in fragility, curves, translate that into strains in pipelines. So how we do that in numerical models, site-specific problems, it's easier than how we do that on a regional scale. So that's a different question to discuss. But I do agree with Tom. I think that strains are very important. And the larger the scale of the problem which we're discussing, the more uncertain it is or how we're gonna solve it. Yeah.
Thank you.
Of course.
Katerina, from your perspective, where you're focusing on advanced numerical analysis for this particular problem, what do you see as the most important thing to really focus on from what you've done?
Having enough information about our site. And when I talk about information, I talk about both site-specific soundings, but also the geological model is really important. And this is something that we ought to be doing, trying to reconcile the both or use the one to constrain the other, because it can help us make some decisions moving forward. And in our case here, I think having a diverse set of data. We had CVTs, but we also had field vein, which helped us constrain the information we had about undering shear strengths. So I know this may be a luxury for certain problems, but at least from the research perspective, we're always trying to shoot for the maximum possible and then see what we can realistically attain in industry projects. So I think, and that's an obvious one, but that always needs to be repeated. And then capable and usable numerical models, both from the system level side, but also from the constitutive model side. I think that is important. So maybe I'm patting my own back, but in this case, we wouldn't have been able to get this if we didn't have this set of tools and the engineering procedures that went with them.
Barry and Jinyan, one of you can start. Is moving forward, when you look at these regional simulations and the software that Dominiki talked about, as well as R2D and OpenSRA, what capabilities are currently missing from your perspective that need to be added to these softwares to make them more informative?
In terms of, let me speak, I wouldn't consider capability, but I would love to have the program be performing more validation exercises. I think that's very, very useful from a developer perspective, especially we're putting all these different models together and trying to run them all at the same time. And we don't expect utility owners and users to rely on us on day one, but we hope that we can perform all these validation exercises over time and give it a confidence that our program can predict something that's useful for you to rely on in a few years. So that's why I think is actually the most important part from a developer perspective.
Jinyan, did you have something to add?
Yeah, I agree with Barry, and just to add a little specific features in R2D. So in R2D, we do not have the high resolution pipeline stream model embedded already. We rely on the users to provide them. And we do not have a standard library for this type of high resolution stream-based models. So I think that's something we need to work on. And also the seismic hazard part in R2D, we have a very good, very well-developed pipeline for California, but when they apply these models to other regions in the world, is not super straightforward. So I think those are something we can move on and push forward.
The remaining people, Tom, Katerina, and Dominika, do you want anything to add in terms of what you think is currently missing in our risk software tools?
Yeah, I'd like to say something.
Yes.
One of the major problems with underground infrastructure, including pipelines and fixtures and appurtenances, is corrosion. So corrosion is just such a big issue that we've tended to stay away from it until we get a certain purchase on the general seismic problems and ground structure interaction and so forth. But one of the things that's really needed on the regional basis is to identify areas of potential corrosion and to be able to model the effects of corrosion on pipelines, to be able to say that we would expect behavior to be within these bounds if you happen to have a corrosion interface or a corrosion problem of such and such a nature. So that's a very important issue. The other important issue is there's a lot of technologies that are being developed to improve the performance of pipelines in situ. So for example, you have cast in place liners and you have cast in place pipes. They both have slightly different structural capabilities, but they are installed by trenchless construction methods as a means to further the infrastructure life of these facilities, but they actually carry a seismic dividend. They can enhance the capabilities of a pipeline to sustain transient motions. They can enhance the capabilities of a pipeline to sustain settlements, differential settlements, and lateral movements associated with lateral spreading and different kinds of deformations that are generated by earthquakes, including landslides and so forth, and fault movements.
And you know what, Dominique, you would like to add anything?
Is there time for me to add?
Yes, you can add something to that, yes.
I was going to say that I think the more we move towards distributed infrastructure and we rethink the way we do engineering on city scales, we have to think about sampling the hazard curve into scenarios, because those differential motions or PGAs or PGVs or whatnot, the intensity measures on a spatial dimension will need to be accounted for. And then those scenarios, how we select those scenarios will be relevant to what facilities or locations or how many balboas we care about. And then every time we sample those scenarios, we can't have Katerina run simulations in the way that she ran Balboa, but we can have surrogate models picking the risk-informed scenarios that matter to us prospectively. Because retrospectively, we can do as many analysis as we can to identify the layers that matter, right, for the damages that happened. But prospectively speaking, we need to be able to select the risk-informed scenarios that we want in order to inform our analysis for future designs. And hazard curves won't do it for those kinds of systems that rely on on relative deformations.
Dominique, I noticed in your presentation, you focus quite a bit on trying to handle the better spatial distribution of liquefaction effects, because both HAZUS and procedures that we have used, for example, that are available, that were implemented in OpenSRA, they tend to say this entire area is going to have liquefaction, when we know after an actual event, maybe only 5 to 10% of the area actually has deformations. And so we tend to overpredict these things. Your idea of using the CPTs and calibrating to it seemed to restrict that. Did you get it down to a sufficient amount of localization, or by the time you do all these different scenarios, was it still relatively broader than you'd actually see in any particular event?
No, it was fairly localized, actually.
Okay.
We actually were able to narrow it down to and compare it with the hold of scenarios that, I mean, it then comes down to basically how granular you can run those scenarios for. It just comes down to computing capabilities. But this is not as nearly as big of a problem as it used to be, right? I mean, the SimCenter has capabilities of that kind.
So when someone asked you a question about did you run the software against case histories and how do things compare? So for example, the Northridge earthquake, if you run that simulation over the entire affected region, does it focus in on?
Yeah. I showed one comparison with the locations that we predicted and the locations that were from the field work, and then it actually localizes at the locations. We didn't we only had one realization
Mm.
shown, so I actually can only run as many realizations as I can.
Yeah.
But you can actually see localizing in areas that the field work was able to pick. And of course, I mean, as I said, my simulations have uncertainty, right? So
Yeah.
I will have to run many scenarios and then have a range of looking, but it localizes in areas that one expects to see susceptibility, and then from there, permanent displacements and lateral spread.
Thank you.
Yeah.
Katerina, I saw your head going back and forth, or yes and no.
Yeah.
So you're probably agreeing with some of what she was talking about. So what would you like to add?
I agreed with what Dominiki said. I mean, it's not efficient. It's not realistic in any scenario to be doing these types of analysis. The one thing they're useful for is for hindcasting. And hindcasting in Balboa showed us that spatial variability for this type of environment mattered. I'm not the first one to say that in alluvial, spatially variable environments, this matters. So it can give us an indication of where we should try and honor it more. If you look, for example, at 1D LVIs for this site, you're going to get a massive number of centimeters just for Balboa 10, that sounding, and almost zero for all the others. And with just a one localized LVI, nobody would have thought that we're going to have such a massive mobilization. We would know that we would have some liquefaction trouble, but nothing like what actually happened, plus the fires, plus the 5 blocks that burned down. So we can get indications of what we can do better and what we can bring into some of the more realistic regional and larger scale models overall. So just honoring what mechanics should we be looking for?
Katerina, did you analyze the 1971 San Fernando earthquake and its effect on Balboa Boulevard?
No.
Okay, so but you showed the importance of modeling the groundwater correctly in 1994. So if that groundwater was significantly lower as suggested, then obviously you get a different answer.
Absolutely.
So
And we did consider different scenarios for the water table. And it's such a discontinuous system, right? You lower the water table just a little bit and it becomes a different system.
And so
Completely.
it's a very brittle system. It's
Yep.
on and off, and that was
Yep.
one of the key issues. And so I know Dominiki talked about using the wells, but there's so much uncertainty in terms of what time of year did the earthquake occur, what is the actual groundwater level in this area, what is the level of saturation, because sometimes the ground beneath the water table is not saturated because you've got a fluctuating water table. In many respects, does anyone have additional things to talking about the great challenge of characterizing the groundwater, which is of paramount importance in liquefaction?
That's why we have logic trees, right? I mean, we were using an annual fluctuation bell curve, and then the global water table for when we didn't have wells, and in between waiting for where we had a little bit of this and a little bit of that.
But
when we had old data, we didn't use them at all, and we had new data, we used them all the time. And when we had kind of medium old data, we used them sometimes.
But as you mentioned, the response of the system at the end is a local response at a particular area that just liquefies or doesn't liquefy. And so much of it has to do with, is the groundwater a meter higher or is it a meter lower? And there's a lot of uncertainty, and it's like a bimodal performance, whether the water's high or low at the time the earthquake occurs at that location.
Right.
Yeah.
That's why I think that's why we have logic trees.
No,
And no?
Well, Tom, you want to add something?
I was going to say a great example of this is the contrast between the 1971 San Fernando earthquake and the 1994 Northridge in the area of the Jensen filtration plant and juvenile hall slide. Because in 1971, you had the utility corridor at the Jensen plant move 3 meters plus. You had the actual naming of lateral spread by Les Yao at the juvenile hall slide. And then so many years later, you have the 1994 Northridge earthquake, and there's less than a meter of movement at the Jensen plant, and there's no movement at all, hardly, at the juvenile hall slide. And why did that occur? Well, they were reconstructing and reorganizing the upper San Fernando Dam area, and they drew the water table down. So the water table was up prior in 1971, and it was down lower in 1994. And you didn't pick up, you picked up movements, but you didn't pick up large movements.
Any additional thoughts? There was one is I really appreciate Dominique, Katerina, the rest of you really responding to the questions. I noticed that as these questions came forward, you sat there and typed out answers and responded to the questions. So a lot of these questions have been dealt with. And I think, Matt, we should make sure we publish the questions and the answers to the participants so that they may have not been paying attention to that nice little dialogue going on the side. But one question that still persists is the buoyancy effect. There was several questions that talked about, did we include the buoyancy effect? You know, often in buried utilities, because of the sand backfill, the high water tables, we have these manholes pop up. We have buoyancy effects on pipeline performance. Do our models or the things we talked about today consider that? Tom?
Yeah, I think when we look at buoyancy effects, we should never forget that work that was done at Davis in the centrifuge for the Transbay tube, where they actually showed that when soil liquefies, there is a sliding and a heave that goes on, but that heave starts to generate negative pore water pressures and things stop. So when you analyze pipelines simply as a buoyancy effect, that is, it's going to rise relative to the material liquefying, you're getting a more conservative assessment of what's going to happen as opposed to what was shown in the centrifuge tests and what actually ended up being the final design for the Transbay tube. So that's very important, I think. The other thing is that buoyancy effects often have their biggest influence on the sewer system. So here you have pipelines that are buried somewhere between, let's say, 3 meters and 5 meters. And there you have this opportunity of failure on the outside of the excavation and rise on the inside and a popping up of the various utilities. You don't find it as much in water supply pressurized systems.
Barry, moving forward, there was a question about what are the differences between OpenSRA and HAZUS? Many people are familiar with HAZUS. There are many issues, so you've got 1 minute to highlight the key issues that are different between HAZUS and OpenSRA, and then I'm going to go to Jinyan to talk about R2D.
I'll say HAZUS is great. It provides a very simple models for you to estimate repair rates for your pipelines. It doesn't necessarily offer an approach for probabilistic analysis of your pipeline network, and that's I think where OpenSRA does very well. Is we allow you to provide uncertainty at every level of your analysis, whether it's in the model, whether it's in the model inputs, the models themselves, or and so you really have you can really propagate the entire uncertainty all the way from the inputs all the way to the end, and get yourself and at the end you will get a distribution of the probability of failure as opposed to just maybe like a singular repair rate that you get from the HAZUS approach. So that is one of the biggest capabilities of OpenSRA is to be able to propagate uncertainty and efficiently.
Jinyan, R2D, and HAZUS comparison?
Yeah, I would say 3 main points. The first, R2D aims to have a higher spatial realization than HAZUS. Secondly, R2D aims to enable higher fidelity modeling. So we are aiming to enable perform some soil structure interaction analysis, Though the example I showed, it doesn't consider that, but our framework aims to enable that for the regional assessment. And certainly in R2D, we look at the interaction of multiple type of infrastructure, from buildings, water pipelines to transportation, and try to look at this community resilience effect.
Thank you. And I'd like to ask for each of your perspective on what's one or two things you can do that we think we can do as a profession to reduce the time gap between research tool development and adoption by industry, especially the pipeline industry that we're talking, water supply and the natural gas pipeline supply industry. Katerina?
So I see two aspects here. The one is the research per se. How does it need to look like, or where does it need to be implemented? And the other aspect has to do with technology transfer as a process, and upskilling as a process as well. On the first part, my perception is that we ought to try and have usable, implementable tools without compromising the level of advancement that they need to have for complex problems. Complex problems deserve to have sometimes complex models. We cannot, steer away from that. But using platforms that are available out there and accessible by practitioners would be ideal. I think offer options like open source implementation, like the ones we saw today, and others that are out there, are also great. And then going to the second aspect, workshops, seminars, dedicated lunch and learns, academics visiting offices and vice versa, 1 day, 2 day workshops, monthly meetings, something regular with commitment, I think would definitely help ensure that in a more timely manner.
Dominique?
So I think I'm going to say the same things that Katerina said, but in a different way. I think we need to release code, working code, plug and play code. Not contact us and we'll let you know. But so in my lab we do that. We post our code open source, and I think to that extent we've migrated to also open source languages, right? We moved away from MATLABs and Flax, and we have our own finite element code, and we have our own finite differences code, and we use Python. To the extent of that, we do that, we always find a resistance on the industry end to use Python. So maybe that's the request on our end would please allow us to do that so that you can use that for free from our side. And the other thing is develop models to our first that use data that is out there. So don't require input that is not available. And the workshops and the evidence, that case histories that demonstrate that our models work are important, but reproducibility of our results, I think, is even more important. So to be able to download the data and repeat what we do and repeat it and get the same results as we do and be able to do it yourselves is, I think, even more important than us teaching you how to do it. And I think there's always something missing when people publish from academia, and I'm as guilty as anybody, but I'm trying to get better.
Okay, thank you.
Yeah.
Tom, last word. We have a minute left.
So I've said it before, if you and your work want to be a change agent, you need to change agencies. And a natural partnership is the public-private partnership. It's the partnership between universities and utilities, which by and large is not developed as much as it could be and not developed as much as it should be. what an academic brings to a agency like a water distribution company or a gas distribution company is correctness, is the best in terms of academia, is new models, it's new education and so forth. But the university people learn a lot from working with the agency about all the practical exigencies, the difficulties in getting things done. And they tend to incorporate this in models that not only deal with the technical aspects of things, but deal with the social and economic side of things. So change agencies, that's what I think is very important.
Okay, and I just want to thank everybody for participating in this panel discussion and your questions, the presenters. And then remember, SimCenter is here for you. And if you're in the research or you're in the industry and there are needs not being met, let us know. And working groups are available. You can get engaged in many different ways. The idea is the National Science Foundation is investing in research infrastructure, including tools to help you teach and perform research and perform analysis more effectively. So I thank you for joining us today and participating in this, and I will now close the session. So thank you.